Welcome to part two. In this section, we're going to do two things. Talk about sort of it graphically using this trade-off. We're going to talk about both graphically using something called isoquants. Then going to move to the table form of how to find the optimal input combination, and then go back to some of the graphics on this input substitution. So we have this term we're going to call isoquant, which is iso means equal and quantity is quant is quantity, so equal quantity. An isoquant is a plot or a function representing all the combinations of these two inputs that produce the same output. So it's 50 pounds of fertilizer and 10 inches of water, 70 pounds of fertilizer and 8 inches of water, etc. All these combinations give you a yield of 200 bushels per acre, for example. Really, the way to think of it is these isoquants are the two-dimensional contour lines of that three-dimensional production hill. We saw the case where you had X and Y and Z or Q vertical, and you had the big hump going up. If you drew the same areas of equal height or elevation and then pushed them down onto the XY plane at the bottom, it would look like contour maps on a contour map of a hill. So what we're going to do here is look at this in theory, then in a table. So here's the idea: input X, input Y. Output Q is equal to some level Q tilde is what I have drawn here. So for example, when you have very little X, you're over here on the left side of the X-axis, well, you have to use a lot of Y if you want to produce whatever Q tilde is, say 17, or let's do corn, and we'll say 200 bushels per acre. You're going to need a lot of fertilizer to compensate for not having very much water. Or maybe you should use seeds. I think that makes more sense. If you're going to use a lot of fertilizer, if you only have a few plants per acre. But then as you increase the number of plants, you can cut back on the fertilizer. And so you can see in the middle here somewhere, you're going to have a reasonable number of plants per acre, seeds per acre, and a reasonable amount of fertilizer. But then if you have a whole lot of seeds, you can maybe cut back on fertilizer and still get that same yield. And that's usually what you see is this trade-off curve is downward sloping. As you use more of one input, you use less of the other one. And the slope gets really steep or really flat on the ends, and in the middle it's somewhere more linear-like. So here's another way to think of it. Here, this example is kind of hokey with swine feeding operation. You got capital in thousands down the one side there in the rows, and then the number of people you're hired per year and how many hogs you would grow. So let's say the first one, you got a small building, only $25,000 worth of a building, and you've got one person working for you. Well, you can grow 500 hogs. You can get through the smaller building. The person's busy doing a lot of work. If you gave that person a second, if you had two people, you can grow double the number. You can get 1,000 hogs. If you had three people, you can get 2,000 hogs. So there's obviously one person isn't enough. You could do more and get a lot more production out of that building. And then you go all the way up to, you can keep going here. And you just go down the line. You have more capital. The building gets bigger. You get more and more hogs out of it on a year basis. It's like I said, the example is hokey, but the idea is maybe I should come up with a better one here with some other numbers. But it's probably seeds and nitrogen, water and seeds per acre, things like that would give you a much more realistic example. But what the idea is what these isoquants are is you're just connecting areas of equal production. So here's like 8 here, 8 here, 8 here, 8 here, and you go down like that. There's 22, 21, 5, 22, 22, 22, 22. You can see they're going to start tracing out these isoquants. 30, 30, 30, 30. There's a whole bunch of 30s. If we go to the next slide here, all I've done is connect these numbers together. And you can see those are the isoquants. There's this output up here, and if you project it down onto the two input case, you can see you get these nice little isoquants, if you will, the areas of equal production. That's all we're doing here. You can do it graphically. You can see the third dimension is hogs per year, and you can see as you go, if you went up there, the isoquants are those contour lines horizontally, and then if you projected them down on the bottom of the box there, you would have this figure here is what you get if you turned it around the right way. So that's what these isoquants are. Well, what is this isoquant? It's actually the ratio of the marginal products. The marginal product of X divided by the marginal product of Y. If you, we'll show you that it's really delta Y over delta X. It's the substitution rate between X and Y at the margin. If you reduce X by the amount delta X, you must increase Y by the amount delta Y to keep your output constant at here, I guess, Q tilde. So you can see if you cut back delta X, you slide this way a little bit, and then you have to go up. You have to increase Y, delta Y, and then you keep output the same. So this is what we're doing here. We're creating input substitution. That's what this curve is. So we call this isoquant slope. It's a line in the xy plane. Well, what's the slope? It's dy dx. That's, you learned that one. Well, dy dx, why not just do the ratio of the marginal products? It's dq dx divided by dq dy. And so if you got the one derivative over the other derivative, that's what the marginal products are. You could take the denominator, which is a fraction, put it up in the numerator and flip it over, and you can cancel out the dq's, and you're going to get the ratio of the marginal products. That's the dq dx divided by dq dy. That's the ratio of the marginal products. Actually ends up being dy dx. And so there's just this minus sign running around, and this is as close as I can get without going into something called the implicit function theorem, and I'm not going to do that. It's not needed for this class. But the slope of that isoquant, the trade-off curve between the two inputs, is the ratio of the marginal products with this extra marginal, or with this extra minus sign running around. And we call that ratio of the marginal products the marginal rate of technical substitution, the rate of substitution between these two inputs. And so that's all this stuff is tied together. We can derive all this from calculus and go back to the implicit function theorem to get this ratio of the marginal products as the slope of the isoquant. But that's what we're doing. That's the graphical way to think of this. That isoquant is the trade-off curve between the two inputs. All along that curve, you produce the same output. And as you move around there, you're substituting between them, and that substitution rate is the ratio of the marginal products. So isoquant slope is the ratio of the marginal products with a minus sign running around. And that's the substitution rate between the two inputs at the margin in the production process. We called it the MRTS. Well, the price ratio is the substitution rate between the two inputs at the margin in the marketplace. So what's the economically optimal? We said the equal margin principle says that the ratio of the marginal products equal to the price of the ratio of the two input prices. So MPX divided by MPY is supposed to be equal to RX over RY. Those two substitution rates are supposed to be equal. So if you look at it graphically, you got your isoquant here, and then you got the slope of that price line. That price line is the ratio is Rx over Ry with the minus sign in there. That is constant. If you take 1,000 pounds of fertilizer in, or 500 pounds, or 800 pounds, it doesn't matter. The same conversion, they always have the same price of fertilizer and seeds. The trade-off between them is constant, so it's a straight line. Whereas you go around in the isoquant, as you have way too few x's, you need a lot of y's. So if you change x a little bit, and then that it's steep, and then it goes down and gets flat at the other end. It's not a constant trade-off curve, is what I'm trying to say. But you can see that point of tangency is going to define the economically optimal point, where the trade-off between the two inputs in the production process is equal to the trade-off in the marketplace. And basically, you draw a line, the trade-off curve, and you have a tangency. Economists get all excited about that kind of stuff. So let's get more realistic. We've been talking about theory. Let's get into some more practical examples here. And so what we're talking about here is going to be pigs, hog. It's a feeder pig ration. Hogs are normally sold at about 250 pounds. Is considered market weight usually now. And so you have feeder pigs. You get them up to us halfway there, 125 pounds. How much more corn and soybeans meal does it take to get them to 250 pounds? Hog rations are primarily corn and soybean meal, shelled corn ground up, and you put in soybean meal. Soybean meal, they take the soybeans and bake them. And it makes the, like you don't eat raw beans. Even if you took beans, and you have to process them. They're not very digestible. And so you end up, they bake them basically, and it gets this thing called soybean meal. It's got a lot of protein, it's got a lot of fat, oil in it, soybean oil. And it's a really good component for a lot of livestock feed rations. And so the way they used to do this is they actually put these in pens of 30 pigs in a pen, and then change their feed rations and get them up to market weight. So in this example, they maybe only gave them 10 pounds of soybean meal, and they let them eat the corn as much as they needed to get to 250 pounds. So you needed 376.8 pounds to get them up to that weight. Whereas you gave them more soybean meal, say 15 pounds of soybean meal, you got by with 20 fewer pounds of corn to get them up there. And then you can see added 5 more, and then see how much corn it took to get them all the way up to the 250 weight. So you can quickly see here, okay, I go 10, 15, 20, 25, 30, all the way up to 70 pounds of soybean meal. And use less and less corn. We get more soybean meal, less and less corn. That plots out this trade-off curve. So which feed ration do I use? When I know how much I pay for soybean meal and I know how much I pay for corn, all these combinations will get me to 250 pounds. Which one is the one to use? How much soybean meal, how much corn? Well, we've done enough in this to think it's going to depend upon the prices. How much does soybean meal cost? How much is corn cost to make that feed ration? Same thing for milk cows. It'd be corn silage and soybean meal or things like that. There's just feed rations are a very common example of this multiple input production process. Well, we know it's going to be a point of tangency here, but we're going to get there in a second. What is the slope of that trade-off curve, the isoquant? It's the marginal rate of technical substitution. As you increase soybean meal, how much can you decrease corn and keep output the same? Keep putting 125 pounds on those hogs. Well, we can't use the MRTS as the ratio of the marginal products because delta Q is 0. Everywhere along there is delta Q is the same. Q is the same. There's no change in Q because what is the marginal product? It's dQ dx divided by dQ dy. And so you can't use there's no dQ. dQ is 0. And so what we end up doing is dQ dx divided by dQ dy, you get the rate, it becomes dy over x, dy dx, or delta y over delta x is the table form as opposed to the derivatives here. And so what's delta x? It's the soybean meal. We're going to label, I should probably label this column as x, and then the second column is y. And then the delta y is just the two, it's like we've done before, except now it's two inputs. So here's this 1.2. How do I calculate it? It's 294.6 minus 300.6 divided by 45 minus 40. 294.6, et cetera. Here, this is laid out. That's where the 1.2 comes from. 1.8 is 289.2 minus 294.6 divided by 50 minus 45, and et cetera. And so the way to interpret this MRTS is as the that's that slope of the isoquant. It's steep and it gets shallow as you go down the slope. If you increase soybean meal by 1 pound and you decrease corn by 1.2 pounds, in this example, if you increase soybean meal by 1 pound, you can cut back in corn by 1.96 pounds. All we're doing is going down this curve and calculating the slope of that as steps. That's what this MRTS is. And then the last part is the price ratio. We know the ratio of the marginal products has to equal the input price ratio. And so all we've done here is the ratio of the marginal products, that's MRTS column, and here's the price ratio. The soybean meal is $176 a ton or 8.8 cents a pound. Corn price is $2.24 a bushel, which ends up being 4 cents a pound. So the price ratio is 0.008 divided by 0.04 or 2.2 pounds of corn per pounds of soybeans. And so you just got to keep everything straight, which is X and which is Y here. Because if you really look here, the ratio of the marginal product of X divided by the marginal product of Y is equal to the price ratio of X, price of X divided by the price of Y. But this ratio of the marginal products ends up being, once you do that, it's dQ dx divided by dQ dy. Once you bring the fraction from the denominator up to the numerator, you have to flip it over. It changes into dy dx, delta y over delta x. And so even though, so change in y over change in x is equal to the price of x over the price of the y. The key I want you to focus in on, it's y change over x change, x over y in the prices. And so there's the things switch. So you have to keep track which one's x and which one's y, but you can see where does the price ratio equal to the subslope, the slope of the isoquant at 2.2, which means here's the economically optimal input feed ration. 30 pounds of soybean meal and 315 pounds of corn. If you change the price of corn and make it larger, your denominator is going to get larger, so this number is going to get smaller, and you're going to go down this way. You're going to use more. You're going to use less corn, and the other way around. It's the way you would slide around in that curve. So you got your isoquant, and then the price ratio is going to shift, and you're just going to slide up and down on the isoquant. So this is our way to take these tables and create marginal rate of technical substitution from the price ratio, tell us which one is which. So you can go through this and think about it more intuition, try to build some intuition here. That ratio minus delta y divided by delta x is how much less y you need if you increase x, which we call the marginal rate of technical substitution, has to equal the price ratio. Well, all I'm going to do here is take this and cross multiply, get that, and you end up with, take both sides times ry and then multiply both sides by delta x. And you get this little statement here. Minus delta y times price of y is equal to delta x times the price of x. So now you've got your, what is minus delta y times the price of y? It's the cost savings from decreasing y. I'm going to reduce my y, that's delta y, take it times the price, that's how much money you save by cutting back on y. What's that got to equal? It's got to be the cost increase from increasing x. You start using more x. Well, what's that? How much more x is it? It's delta x times the price of x. So what you're going to do is keep sliding down that isoquant, decreasing y and increasing x. All the time, output staying the same. And so you're going to keep coming down that curve, decreasing y and increasing x, as long as the cost savings exceed the cost increase. So it's like a partial budget analysis again. As you come down the curve, you go, how much do I save when I cut back on y? How much I have to increase x? Oh, I cut back on y by $10 and I have to increase x by $3. Oh, okay, that's worth it. Now I cut back on y $10 and I have to increase x by $8. Oh, okay, that's still worth it, but boy, it's getting closer. Decrease y by $10, increase x by $10. Okay, I'm breaking even there. Now I stop. That's all we're doing. It's a partial budget analysis. You're sliding down the isoquant until you find the spot where the price ratio is equal to the marginal rate of technical substitution, delta y over delta x, or where the cost savings from decreasing y just equal the cost increase from increasing x, which is essentially as you go down the curve, your MRTS gets smaller and smaller, but the price ratio stays the same. You just keep coming down there until you break even, and then you stop. So main point on all this is when you have information on inputs needed to generate these same output combinations, you can identify the economically optimal input combination. Done it in the theory side with the ratio of the marginal price equal the price of the inputs. We call that the equal margin principle. How do you do it in practice? You go through this isoquant slope, the change in y with the change in x with the minus sign in front of it has to equal the price ratio. We just showed that. The key there to note is it's delta y over delta x, the price of x over the price of y, the unit, the inputs change, delta y over delta x, price of x over price of y. And the way to think about these tables, yes, I know they're kind of hokey and silly, but in the end, underneath them, where those would really come from is there is a two-input production function out there that could describe and give you that table. And that's what I mean by this last statement. The numbers in the table, like I've created, actually have underneath them a two-input production function. So let's do a think break here. This one is rations of grain and hay that put 300 pounds of gain on 900 pound steers. You're getting them ready for market. How do I put that last 300 pounds on them? You should be able to do this think break. I would pause and work this one out. But here's the marginal rate of technical substitution. How do you calculate this 2.93? What would be here? Same thing. How would you fill in this next MRTS? And then the price ratio. How do I figure out how much grain and how much hay to feed my cattle? So if grain is 4 cents a pound and hay is 3 cents a pound, what is the economically optimal feed ration? I would recommend labeling which one is X and which one is Y so you get the price ratio right, and then do your MRTS and calculate the price ratio and then figure out where the economically optimal feed ration is. We'll come back in a second. All right, so I work out the example here. Like, how do you calculate this 2.6 I give here? It's the change in hay, 935 minus 1130, divided by the change in grain, 975 minus 900. And then here's where the minus sign comes in and gives you the positive number, because you can see this numerator would be negative. So that's where 2.6. Go down here, the 133 is 525 minus 625 minus that, divided by 1200 minus 1125, and you get that price ratio of 1.333. Where do I get the price ratio? It's the change in hay over the change in grain. So it's the price of grain, 4 cents, divided by the price of hay, which is 3 cents or 1.33. Where that equal is right here. You can see if corn got a little more expensive, or I should say grain, instead of 4, it would be 5/3. 5/3 would be somewhere up here. 5/3 would be 1.66. So it would be right in the middle here somewhere. It'd be, you'd be right in this area here, above this 1200, below the 1125, above the 525, and below the 625. So it'd be in here somewhere. It'd be 1.67. Let's say the price of grain went up to 5 cents a pound. you can change the price ratio. But you can see how this would work out. Calculate this MRTS, that slope of the isoquant in delta form, and then you have the price ratio. Where is those two equal? And you find it in the table. That gives you the sense of how to calculate the economic optimum. It's 1,200 pounds of grain and 25 pounds of hay. So we've talked about identifying the economically optimal input combination using this table, tabular data, and prices. You need to input data on the isoquant. You need to know the different feed rations that generate that same amount of gain or the same milk production. And we use the calculus again. We're going to use that to fill in those gaps. We got the table form, but that last example I worked is what are you doing is 1.67, 5/3. Well, you can see quickly we can underneath these numbers, the grain and hay that make that table, there's going to be some production function. Let's use that and do calculus instead of making these hokey tables. But before we do that, I want to kind of go through these different types of substitution, more think broadly about substitution between inputs. And we're going to talk about 3 types of substitution. There's going to be perfect substitutes. That's the one on the bottom left here, where the isoquants are actually straight lines. Imperfect substitutes, that's what we've been doing already, corn and soybean meal and feed ration, for example. And then you have non-substitutes or perfect complements where they don't substitute at all. It's like I always think of tractors and drivers. You can have 3 drivers, but if you only have 2 tractors, it isn't going to do any good to have that extra 3rd driver. You get isoquants that are actually right angles. They just come down, bend over, and they just make a corner, if you will. It's a right angle. So types of input substitution, I think probably the perfect substitutes are certain kinds of feed, sources of feed. Soybean meal and canola meal are good examples of corn and sorghum, wheat and barley in feed rations. Up north, Canada is one of the world, I think it is the world's largest canola producer, and there's a lot of canola meal left over and available. So as you go further up there, feed rations for cattle, for dairy cows, for hogs, you can use canola meal instead of soybean meal. It's another high oil seed, lots of protein, lots of fat. There's some conversion between them. 1 pound of soybean meal is equal to 2 pounds of canola or something like that. Another one, as you go further south or out in the plains, like places like Kansas, western Nebraska, down into Texas, Oklahoma, instead of corn, they grow sorghum because it's more drought tolerant. But again, they're very corn. The price of sorghum is actually based off the price of corn because they're very close substitutes. And so in feed rations out there, you might use sorghum instead of corn. It will be a constant rate of conversion between them. The same with wheat and barley. In some parts of the country, they use wheat or barley. As you go further north, barley does better. You might switch over to barley as part of your feed ration instead of wheat. And we've done these imperfect substitutes, corn and soybean meal. There is some substitutability between them, more carbohydrates and a little less protein and fat. Which way do you want to go? You kind of have those big macronutrients of carbos, fats, and oils and proteins, how you can trade off between them and still gain weight for an animal. And then the last one is, the tractors and drivers is probably a good example there. So I've kind of gone through this one verbally already, these perfect substitutes. You just have to know the conversion factor. Is 2 pounds of canola meal is 1 pound of soybean meal? I have no idea if that's true. I just made it up. But the slope of the isoquant is change in canola over the change in soybean. Put a minus sign in there. It's going to be 2. You cut back on soybean meal by 1 pound, you're going to need 2 pounds of canola meal, or whatever the conversion factor is. Each animal might be different. Same with sorghum and corn. Maybe it's 1.2 bushels of sorghum per 1 bushel of corn in a feed ration for beef cattle, for example. And so the conversion, the slope of the isoquant will be 1.2. What you'll notice is this: it doesn't matter. There is no, it doesn't change. The isoquant is going to be a straight line. And so what's surprising here is that the MRTS equal to price ratio still applies. It's just what happens is you end up on one end or the other. So if the MRTS, the slope of the isoquant, is some number K, 2, like I did with canola, well then if the price ratio is less than that K, you're just going to use only soybean meal. If it's greater than that, then use the other one. So if canola gets cheap, then you use canola. If otherwise, soybeans are cheap, you use soybeans. And if they're exactly right on that trade-off curve, it doesn't matter how much you use. So you can kind of see here's the graphics of it. In this example here, you're either going to be on this end of the isoquant or this end of the isoquant, or if they're equal to the trade-off and the production function is equal to the market trade-off, it doesn't matter. But this black line that goes between the corners, or across the ends, that is the isoquant. It's a straight line. There's no curve. It's a straight trade-off curve. The production process, there's a constant rate of trade-off. They're perfect substitutes. They just have a conversion factor between them. So in this example here, you don't use any soybean meal, you use canola because canola is cheap. Price ratio is really steep. Then you come down here to the other end, the price ratio is really flat. That's just a way of saying that soybean meal is relatively cheap compared to canola, so just use soybean meal. And then if the price ratio is the same as the slope of the isoquant, it doesn't matter. Canola, it costs twice as much as soybean meal, and so it doesn't matter if you buy soybean meal or canola. You need twice as much canola to put the rate of gain on the animals, and it costs twice as, or half, and so half as much, and so it works out fine. So the method still works. It's just kind of funny. You end up on the points usually. We've done this one already where you have an imperfect substitute where the substitutability changes as you have different amounts of each of the two inputs, and you get the trade-off curve like I've drawn here, steep, and it gets shallower and shallower until it's flat. And the price ratio moves around, you just move around on that trade-off curve. The last one is this the imperfect complements where there is no substitution. The two inputs must be used together. Without the other input, neither input is productive. They must come together, tractors and drivers. If you're trying to till the field, it doesn't help if you only have one tractor and 10 drivers. You can't get any more tilled. Fence posts and wire. I mean, tractors and drivers is an easy example, but maybe shovels and people to dig with them and stuff like that. But the other one that shows up in more practical sense is chemical reactions. There's a lot of chemical reactions where it goes at the rate or the amount of whatever limiting one there is, whatever the two chemicals that are reacting. It doesn't matter if there's a whole bunch of the one, it goes until it uses up the one that's limiting. And so a lot of those are that are this kind of, you can't add more of the other input, the other chemical to make more. It just it stops. And what that does is that the isoquant is a right angle, and the MRTS is undefined. It doesn't really identify the solution. You end up with something that looks like this, where the price ratio, you're on the point, and no matter what the price ratio is, you're still on that point. It doesn't do you any good to go up higher and have more drivers or have more tractors in the same number of drivers. One driver and 5 tractors, or one tractor and 5 drivers. It doesn't matter. The price ratio doesn't matter what the wage rate is or anything like that. And this is what we call a Leontief production function. There's a mathematical way of writing it. Q is the min of some factor A times the X input plus some factor B, or B times the other input. And what happens here is you have an output quota. I need to get the field plowed in 6 hours. Okay, how many tractors and drivers do I need? Or you have a budget. I've got $1,500 to spend on plowing. How much can I get done? That's what you end up using everything in fixed ratios.